Hi, it's Isaac from SFIA. When you're done with today's episode, check out Jupiter Brains and Megaminds, a look at impossibly big intelligences we might engineer or even become one day. Just go to go.nebula.tv/IsaacArthur and use my code IsaacArthur. As our world's energy demands soar, the future depends on revolutionary ideas. Today, we are exploring the game-changing technologies that could power tomorrow and redefine what's possible. Welcome to our first episode of the year, and of the 11th season of Science and Futurism with Isaac Arthur, bringing you a weekly glimpse of our crazy and awesome future since 2014. If you're new here, I am your aforementioned host, Isaac Arthur. I am a physicist by training and a third-generation sci-fi geek. And something we do a lot here is try to use science fiction concepts and ideas to explain real-world ideas and technologies. From the near future to times so distant even the stars themselves are but a memory. Our focus for today is upcoming energy technologies, and that will be everything from tomorrow's tech to those that might generate power at the end of the universe. You can see a list of those subtopics up on the screen, and feel free to jump directly to the topics of interest to you. But we cover a lot of topics, from aliens and megastructures to artificial intelligence and cybernetics, and the civilizations that might arise around them or through them. Space is one of our biggest focuses, and I have the honor of being the recipient of both the National Space Society's Excellence Award and Pioneer Award, an honor I share with Elon Musk, Kip Thorne, John Glenn, Ray Bradbury, Jared Isaacman, and many more folks who deserve the honor a lot more than I. I am also the president of the NSS since 2022, which still humbles and shocks me at times. I am not a big one for autobiography, but it's important to mention your background occasionally when you're getting ready to tell people tons of information with an implied, "Trust me, I know what I'm talking about." And I'm also grateful that many of our audience members have volunteered over the years to help edit and brainstorm our scripts to help keep us accurate and cutting edge. Also, if my somewhat atypical accent and speech impediment is giving you some problems, every episode of this show has transcripts on it in the subtitles. What else is there? I am 44 years old at the time of this writing, a U.S. Army veteran. I am married to my wonderful wife Sarah, and reside on our farm in Northeast Ohio with our 3 children, Christopher, Isabella, and Geometry, ages 9, 8, and 6, whom we also homeschool. I credit coffee for my ability to juggle all that. It's the fuel that keeps me going. Of course, the fuel that keeps our civilization going, in addition to caffeine anyway, is mostly dead dinosaurs, and has been for a century and counting. Actually, we think it's mostly dead algae and plankton, but either way, we'd like to move beyond those for many reasons, and we are in the process of developing and deploying many awesome technologies to help with that, which we'll be looking at today, and there are a lot of them. Since it is a big topic and for the sake of brevity, we will be keeping discussion of each section short. This is especially true of topics where we have a focused episode. And in the hundreds of episodes of SFIA, we have done quite a few that deep dive this or that type of energy, from the modern and mundane to the distant and theoretical. When we touch on one of those, we will reference the appropriate episode for those wanting a deeper dive, but we would be remiss if we didn't bring them up. We will be covering, briefly, some of those very advanced energy ideas towards the end of the episode, and those are fusion, antimatter, matter-to-energy conversion, perpetual motion machines, vacuum energy, black hole energy, dark energy, zero-point energy, and tapping multiverses. But before we get to those more speculative areas, we'll be covering more grounded stuff, like energy from the ground itself, and looking at advanced solar technologies, next-generation nuclear, hydrogen fuel and storage, energy storage innovations, bioenergy and synthetic fuels, smart grids and energy efficiency, geothermal, and other alternative sources. That's a lot to cover, so a drink and a snack might be a good idea. Advanced solar technologies. Any discussion of emerging energy technologies needs to begin with solar, as it's probably the most promising these days. And while I am a big fan of space-based solar power, that is something we've discussed in its own episode, and will be deep diving more in the future, so instead I'd like to focus on perovskite solar cells, transparent and flexible solar panels, and CSP, concentrated solar power. Traditional silicon-based solar panels have already made significant inroads into the energy market, but several emerging technologies could revolutionize how we harness sunlight. Here's a closer look at some of the more promising developments. Perovskite solar cells are one of the most exciting advancements in solar technology. The technology has been developing for some time and making improvements to the problems they've had with service lifetime, scaling up for manufacturing. So hopefully should be moving into the regular market this decade. This will offer higher efficiency and lower manufacturing costs compared to traditional silicon cells. Hopefully. The key component in these cells is a compound with a crystal structure similar to that of mineral perovskite, hence the name. These materials are highly effective at absorbing light, which allows for thinner and lighter solar cells to be manufactured at a fraction of the cost. Perovskite cells have already achieved efficiencies of over 25% in laboratory settings and 29.8% for tandem perovskite silicon devices. Additionally, perovskites can be tuned to absorb different wavelengths of light, making them ideal for those tandem solar cells. These are multi-layered structures that capture more of the solar spectrum and thus improve efficiency, so one layer might be able to absorb red light and the layer below blue or green. Again, the main challenges are improving their long-term durability and stability, as they tend to degrade when exposed to moisture and heat. However, researchers are making significant progress in enhancing the lifespan of these cells, bringing us closer to commercial viability. Lifetime and durability are weaknesses of solar that have been improving rapidly, and one of our other issues with getting solar into the wider market is the desire for transparent and flexible solar panels. Unlike traditional panels, these can be integrated into various surfaces, including windows, greenhouses, vehicle roofs, and even clothing. Transparent solar panels are obviously not 100% transparent to light, since light is what runs solar, but this can either be done by absorbing wavelengths we can't see by, like ultraviolet and infrared, or by reducing light coming through like tinted windows do. This may make them ideal for use in urban environments where space for conventional panels is limited, and as an example, a transparent window in an urban apartment in the summer could remove some of the light warming that room while generating power to run air conditioning. Flexible solar panels, meanwhile, open up possibilities for portable and wearable applications. They are typically made using thin film technologies that can be rolled onto flexible substrates. This could enable solar power on curved or irregular surfaces, like the roof of a convertible car or someone's coat, letting them recharge their portable devices. We'll discuss batteries later, but if you imagine someone's clothing having a few small battery packs in it and wireless chargers in a pocket or two, then a lot more portable devices become practical and more lightweight. It would also open the door to options like a circulating system inside them, quietly pumping a fluid around to help warm or cool someone. Speaking of heating fluids, concentrated solar power, CSP, is a technology that uses mirrors or lenses to focus sunlight onto a smaller area, typically to heat a fluid that drives a turbine to generate electricity. Unlike photovoltaic solar panels, which convert sunlight directly into electricity, CSP systems rely on heat energy, making them more akin to traditional power plants. CSP has the advantage of being able to store thermal energy, which allows for electricity generation even when the sun isn't shining. Recent advancements in CSP include the use of molten salt as a heat transfer and storage medium, which can retain heat at high temperatures for extended periods. This enables CSP to produce electricity on demand, addressing one of the primary challenges of solar power, intermittency. CSP systems are particularly suited for regions with high direct sunlight, such as deserts, where they can provide consistent and reliable power. This also makes it potentially useful in cooler tundra locations. While CSP currently represents a small fraction of global solar capacity, it holds significant potential for large-scale, grid-connected solar power. Next-generation nuclear. We can't discuss emerging technology without looking at fission or fusion, but we did an episode looking at developments in fusion technology just a couple months back, so we will bypass that today, beyond noting that while fusion is still a ways off commercially, huge amounts of progress have been made on the basic technology in the last decade, and there's a lot of room for optimism on fusion. The two big ones folks discuss for nuclear fission, on the other hand, are thorium reactors and SMRs, small modular reactors, and those also both have their own dedicated episodes, and recently enough that there's no reason to update them yet. Thorium fission is very much still an emerging technology, while SMRs are actually getting built, and it's hard to say how prolific construction of them will be in 10 years. Nuclear has improved vastly in recent decades, and public fear of nuclear seems diminished, but at the same time, the improvements to solar during that same time span have been greater. For my part, I still think a mixed solar and fission economy would be our most optimal economic build with current technology for producing cheap and abundant energy without the scarcity or environmental concerns involved in fossil fuels. But fission plants require large build times and investments. This is the main advantage of SMRs. They can be built in the tens of megawatts range and built off-site and brought in for quick assembly, so may represent the future of nuclear power. There's also still the reality that no matter how good solar gets, it doesn't work if it's dark or cloudy. Thus you need to find a power supply that works at night or in a storm, like nuclear, or you need to store energy in an efficient and cheap fashion. Hydrogen fuel and storage. Batteries are both expensive and fairly inefficient, even lithium batteries, which are an order of magnitude better than prior batteries. They lose 10 to 20% of the power pumped into them while charging, as heat, and while efficient in discharge, still lose another 2 to 5% running your device. You can also lose another 5 to 10% on converting the battery's DC current back to AC current. So the moment you opt to store power from something like wind or solar, rather than send it directly to people's homes or appliances, you're losing somewhere between an eighth to a third of your energy. Unlike many other batteries, lithium leaks power slowly, 1 to 2% of their charge a month versus 3 to 5% for lead-acid batteries, so they are fine for storing power overnight or even for cloudy weeks. More is always better, but you have to build and maintain that supply and keep them charged the whole time, or else they aren't ready when bad weather comes. Chemical fuels, on the other hand, like gasoline, are a lot more shelf-stable, and since they already exist, we don't have to pay a fee to make them, just pump them and refine them, which admittedly is also a non-trivial cost. But we can instead take water, which covers this planet, and through electrolysis crack it free into hydrogen and oxygen. This is amazing fuel and our preferred one for rockets, except that hydrogen is very tiny and leaks easily and corrodes tanks. Graphene, that miracle substance for building space elevators and strengthening concrete, also makes a good liner for fuel tanks full of hydrogen. So hydrogen fuel storage is looking more attractive, even though you typically only get about 60 to 80% of the energy you put into electrolysis in water out in terms of combustible hydrogen fuel. Then when burning fuel, you only get 20 to 30% out of your typical combustion engine, while hydrogen fuel cells do more like 40 to 60%. But large tanks you can line and then basically fill with water you split into hydrogen using solar or nuclear or whatever, and which you can leave sitting for long periods, may still be cheaper than batteries. It's also useful in aerospace outside of rocketry because hydrogen is incredibly energy dense. A rocket has to carry its own oxygen with it, and 89% of the mass of that hydrogen and oxygen is that oxygen, just 11% is hydrogen. Batteries are even heavier in terms of energy density, a megajoule a kilogram or less, compared to dozens of megajoules a kilogram for most chemical fuels we use. We don't care about weight for stationary energy storage sites for our power grid, and honestly it's not too big a deal even for automobiles, but weight is a big deal in aerospace, and planes and jets don't need to carry their oxygen like a rocket does, they can just breathe in the air. So all they need to carry is hydrogen, which has an energy density of 142 megajoules a kilogram as a combustible fuel, and 120 megajoules per kilogram when used as a fuel cell, both more than 100 times the density of even the best lithium battery. Incidentally, if you're not clear on what hydrogen fuel cells do compared to hydrogen combustion, both operate by combining hydrogen and oxygen into water, but the fuel cell does it by electrochemical reaction rather than by combustion. Within the fuel cell, hydrogen atoms are split into protons and electrons. The electrons flow through an external circuit to generate electrical power, while the protons move through an electrolyte to recombine with oxygen. There may be one type of energy and energy storage that ends up totally dominating, but at the moment things seem to be developing toward a fairly wide mixture of options for both that would vary by location. Both are excellent fuels for vehicles, easily beating out even gasoline for driving an engine, assuming you got an abundant and cheap hydrogen production and storage process. Achieve both and you have a renewable, carbon-free energy supply that would increase vehicle mileage over what an equal weight of gas or batteries permit, and efficiency always goes up if your fuel weighs less for the same energy, since you have to push that fuel around until you use it, burning up more fuel. Whether by fuel cell or combustion, you could use nuclear and solar during sunny days to produce hydrogen for storage with your surplus. You can throttle a nuclear reactor, though depending on design it's fairly slow, a few percent a minute being on the fast end, and we usually run them at continuous levels as our baseload power providers. In a mixed solar and nuclear economy, you might throttle your nuclear during sunny weeks or aim for doing your maintenance in those periods. Regardless, when night or storms come, your nuclear is still going at full capacity and generally power demand goes down. People use less power at night, and even in storms the demand for cooling drops. You cover your gap with that hydrogen since it is relatively light compared to batteries. You can have pipelines, ships, rail, or tanker trucks moving hydrogen from spots with a surplus to those running a deficit. And these might be temporary surpluses or deficits based on weather, season, or equipment failure, or you might have regions that were advantaged on solar or nuclear power production and regularly overproduced to ship to places that ran temporary or even regular deficits. This again is also likely running your vehicles at this point too. Fundamentally, this technology is dependent on how good we can get at cheaply storing hydrogen gas, and again, graphene looks very promising here, but also looks promising for battery technology for enhancing energy density, battery lifetime, and charging and discharging rates. Needless to say, improvements in recycling batteries or manufacturing them cheaper will help with battery storage costs, but a graphene-enhanced battery contrasted to a graphene-lined fuel tank is an example of how, ironically, improvements in one technology can make it profitable only to be undone because of an improvement in a rival technology that made it even better. This happens a lot in energy technologies, where they've all been making massive improvements and often revolutionary changes that people spent decades of brilliant and hard work on, but come to naught because other people's brilliant work improves some other tech too. All I can say on that issue is if you're going to have a problem, being blessed by too much clever innovation in too many areas is the kind of problem we want to have. Energy storage innovations. There are a lot of other technologies besides hydrogen or lithium batteries we can use for storing energy. Molten salts, solid-state batteries, flow batteries, compressed air, and liquid air are some of the most promising options. Molten salt storage. Molten salt energy storage is often used in conjunction with concentrated solar power plants, where sunlight heats salt to high temperatures, allowing it to store thermal energy. This stored heat can then be used to generate electricity even when the sun is not shining. Molten salts are cost-effective and can retain heat efficiently over long periods, making them well suited for large-scale energy storage, particularly for renewable energy sources that need to bridge gaps in power production. The name tends to imply something volcanic, but while they can be big, you could have units no larger than a water heater and no more dangerous. Solid-state batteries. Solid-state batteries replace the liquid or gel electrolyte found in traditional batteries with a solid electrolyte, which can improve safety and energy density. These batteries are less prone to leakage, fire, and thermal runaway, making them particularly appealing for electric vehicles. Solid-state batteries can potentially offer faster charging times and longer lifespans than lithium-ion batteries, though they are still in the developmental phase and face challenges in terms of cost and scalability. Flow batteries. Flow batteries store energy in liquid electrolyte solutions contained in external tanks, allowing them to provide scalable energy storage. The energy capacity of a flow battery is determined by the size of the tanks, which makes them ideal for large-scale storage applications. They are particularly well suited for grid storage because they can discharge for extended periods and have long cycle lives, but their relatively low energy density means they are less suited for portable applications. Compressed Air Energy Storage, CASE. CASE systems store energy by using electricity to compress air, which is then stored in underground caverns or large storage tanks. When energy is needed, the compressed air is released, heated, and used to drive a turbine to generate electricity. The basic technology is similar to the air compressors many of us use for running tools. CASE is advantageous for grid-scale storage due to its potential for large storage capacity and relatively low cost, though it requires specific geological conditions for underground storage and has relatively low round-trip efficiency. Liquid Air Energy Storage, LACE. Liquid air energy storage works by cooling air until it becomes a liquid, which can then be stored in insulated tanks, such as the liquid nitrogen tanks you may have used in a chemistry or physics class. When energy is needed, the liquid air is allowed to warm up and expand, driving a turbine to generate electricity. LACE systems have a long storage duration and can be built at any location, offering a promising option for large-scale, long-duration energy storage. However, their efficiency is somewhat lower than other storage types, and they require significant cooling infrastructure. Each of these technologies offers unique benefits and trade-offs, making them suitable for different applications and storage needs, as well as certain locations or industrial sectors, particularly in the integration of renewable energy into the grid and improving energy resilience. Speaking of the importance of air, in my next video of the Fermi Paradox series, we dive into the role atmospheres play in shaping the emergence and survival of intelligent life, and how they may answer why the stars remain silent. Could the key to solving the Fermi Paradox be hiding in plain sight, drifting in the air of distant worlds? While you're at it, I want to suggest checking out Faithless, a Sojourn story, a feature-length audio drama. Follow Castian Vadrak, a former Inquisitor turned fugitive heretic, as he uncovers the ancient truths in the Sojourn universe, featuring an awesome cast of voice actors, including Emma Gregory, who some of you may remember as Inquisitor Amberly Vale from the excellent Caiaphas Cain audio dramas. Sojourn Faithless is an unprecedented audio cinematic experience. All previous series and videos are exclusive to Nebula for less than $3 a month. All exclusive content is now streaming on Nebula, where all SFIA episodes air early and ad-free, alongside tons of exclusive content from myself and other creators. Sign up at go.nebula.tv/IsaacArthur using my code IsaacArthur to get 40% off an annual membership. That's less than $3 a month, and you'll be directly supporting this show. Nebula also offers lifetime memberships and gift cards, so you can share exclusive content like Faithless and SFIA's monthly specials with friends and family. And now, back to the future. Bioenergy and synthetic fuels. Another way to store energy is to take sunlight and put it in a plant, then turn that plant into fuel, and biofuels remain a good operation for generating portable fuel supplies as a rival to gasoline. Gains in this technology are mostly about finding or creating better biofuel crops, better growing techniques, or improving manufacturing costs. Fundamentally, biofuels are not very efficient compared to solar panels, or energy dense compared to hydrogen or fossil fuels, and so I tend to think they can only work where we are taking advantage of growing or harvesting them where we wouldn't put solar panels or farms. We won't spend too much time on this topic, but algae-based biofuels remains a promising one in my opinion, since we could farm it on the near-dead stretches of deep ocean out from the coast. We discussed oceanic farms more in our recent Ocean Habitats episode, so see that episode for why and how we could do that. So too, waste-based energies, like harvesting a landfill for power, is an example of how you can take the expensive process of getting rid of waste and instead produce energy off it. Smart grids and energy efficiency. Speaking of waste, a lot of gains can be made by just limiting waste and improving efficiency, and that's where smart grid and artificial intelligence can help us a lot. Smart grids and energy efficiency technologies help optimize electricity generation, distribution, and consumption, reducing waste and improving reliability. By using sensors, advanced metering, and real-time data analytics, smart grids can monitor and adjust energy flows to better match demand. Artificial intelligence, AI, further enhances this by predicting demand patterns, identifying inefficiencies, and integrating renewable sources. Additionally, AI support demand response programs, where users reduce consumption during peak times, helping to lower the need for extra power. Together, smart grid and AI make energy use more adaptive, sustainable, and cost-effective. Geothermal and alternative sources. We discussed primary technologies like solar and nuclear and various storage and usage improvements, but there are many other possible power supplies. We'll get to the really high-tech and even scientifically dubious ones in a moment. But first, let's talk briefly about geothermal, tidal, and wind power, all of which we already have. Now, geothermal can include passive geothermal and help control heating and cooling costs, and this technology relies mostly on improvements to digging, drilling, or excavating, in tandem with superior piping systems in terms of cost and lifetime. All of these have seen, and will continue to see, big improvements, so incorporating passive geothermal into homes in the future may grow much cheaper and easier. But we also have advanced geothermal systems that represent a significant advancement in geothermal energy, enabling access to heat stored deep beneath the Earth's surface in areas beyond traditional geothermal hotspots. Unlike conventional geothermal, which relies on naturally occurring hot water or steam, EGS can generate electricity by injecting water into hot, dry rock formations and then extracting the heated water. This process effectively expands geothermal energy's reach to a broader range of locations, allowing for more widespread adoption. Recent advancements in drilling and fracturing technologies have improved the efficiency and feasibility of EGS, making it a promising option for scalable, baseload renewable energy. That's Earth, but how about water? Ocean-based tidal and wave energy harnesses the predictable movements of tides and the kinetic power of waves to generate electricity, offering a consistent and renewable energy source. Recent developments in underwater turbines and wave energy converters have improved the efficiency and reliability of capturing this energy. Tidal and wave energy systems can be particularly valuable for coastal regions as they provide a steady supply of power and are less variable than solar and wind. While still in the early stages of commercialization, advancements in these technologies are making ocean energy a more viable contributor to the renewable energy mix. We also have air-powered kite and high-altitude wind energy systems that use tethered kites or airborne wind turbines to access stronger and more consistent winds found at higher altitudes. These systems can generate more power than traditional ground-based wind turbines by reaching altitudes where winds are both faster and more constant. Airborne turbines or kites, equipped with small generators, convert wind energy into electricity and transmit it down through their tethers. Needless to say, the same technologies that might make space elevators possible for transport of cargo and electricity would make these work much better. You might also be able to then place them far above where birds fly. This approach also requires less material and land than conventional wind farms, which makes it a cost-effective and versatile solution for expanding wind energy in areas where traditional wind turbines might be impractical. That's all our major technologies that appear plausibly on the horizon for the next decade, or maybe a generation or two for things like fusion. Let's finish today by briefly exploring some far further horizon technologies, though of course, we might only be one clever Einstein or Da Vinci away from any of these being constructed tomorrow. Black hole energy. Black hole energy technologies were topics of 2 episodes last year, the first looking at using larger black holes, where energy is harvested by dropping matter into them and generating up to 20 to 40% matter to energy conversion, more than an order of magnitude better than fusion and 2 orders better than fission, and nearly 1 billion times better than chemical fuels. And this is a fairly low-tech, if brute force approach to power generation that mostly suffers from no black holes being near us. No advanced tech is needed, except if you're trying to make those black holes yourself. The second was on the Kugelblitz black hole, which is more like a battery, and where you create very small black holes, atom-sized ones, and as they decay, gather their Hawking radiation for power. See those episodes for more details. Antimatter. Antimatter is a simple enough technology. When an antiparticle hits a regular particle, they annihilate and typically produce a pair of photons of very high energy gamma rays, which then hit other particles and heat them up so they either emit longer wavelengths a photovoltaic panel could absorb or heat water to turn a turbine. Using it is child's play. Storing and creating it is much harder. See our antimatter factories and uses episode for a deep dive on that. Matter to energy conversion. A nice thing about antimatter is that it converts both itself and equal mass particle into energy, so you actually get E equals 2 mc squared rather than just E equals mc squared. But it's rather explosive, and of course you don't get that double for free as a rocket propellant since you need to carry an equal mass of regular matter with you, maybe outright using the antimatter storage tanks as that regular matter mass. In any event, 1 pound has 41 million billion joules in it, and 1 kilogram 90 million billion, making them almost a billion times more energy dense than normal chemical fuels. It may be possible to convert regular matter into energy without an antimatter collision, and if that's the case, then such a converter will match antimatter, but presumably avoid its hazards. You feed regular matter into it at a rate of energy you need, and only when you need it. With the typical US household using about 38 billion joules of electrical energy a year, 1 pound of matter would last just over 1 million years, and 1 kilogram close to 2.5 million per household. This would seem to make it the ultimate power supply if we could make it work, outperforming black holes and matching antimatter, but without the difficulties of creating and storing it. Sadly, unless you count feeding micro black holes to harvest their hockey radiation, we have no clear paths to this technology. Vacuum energy and zero-point energy. I should note that the means by which a black hole evaporates and creates power is often better envisioned as that hyperdense object cracking space-time and letting vacuum energy leak through, which in the process lowers that mass. But we believe there is more energy in the true vacuum underneath this universe than all the matter and energy in it, and we discussed various means of tapping them in our episode Vacuum Energy and Zero-Point Energy, along with concerns that such technology might accidentally destroy a given region of the universe. But since matter-to-energy conversion relies on matter in this universe, and most of the energy in this universe isn't in regular matter, but dark matter and dark energy, it's not as big a supply as it sounds like, and will be dwarfed by the vastly greater energy of the vacuum, which we think underlies everything, making it a better power supply. Perpetual motion machines. Of course, an even better power supply would be one that produced energy endlessly with no fuel, and if you can make such a machine, generally what we call a perpetual motion machine or device, this obviously becomes your very best power source. Eternal energy, from the wheel that keeps spinning even when moving through the drag of air or the friction of axle or dynamo. Now, as the great Robert Heinlein liked to say, "Tan Staffel," there ain't no such thing as a free lunch, and as you might have heard, the U.S. Patent Office refuses to patent any design for one without a working model present. I wouldn't advise folks to hold their breath on getting free energy out of nowhere. Nonetheless, we should keep in mind that the energy this universe contains had to come from somewhere, and occasional hand waves by theorists about everything maybe negating out suffer from a total lack of evidence supporting that, and also implying that a positive sum and a negative sum, while adding up to zero, is actually nothing. This would seem no more true than saying that a business that generated zero net income in a given year did nothing, even though it's been producing and using stuff left and right. It's a philosophically and metaphysically dubious claim we discussed more in our episode on the Fermi Paradox and the Fine-Tuned Universe, though admittedly it's got exactly as much evidence for it as any of our other origin ideas, which is to say, none. For now, we only know that our universe contains stuff, and that if it presumably came from nowhere, then maybe that process, or a more scaled-down version, could be replicated to produce free energy. Nor can we simply wave to the law of energy conservation, which has been cracked if not broken since Einstein unveiled relativity, and which further has to deal with not just the Big Bang, but all the dark energy coming from nowhere or leaking in from somewhere. Dark energy. Dark energy seems to produce new bits of space-time everywhere and at an accelerating rate. We know little of this, so it may be that fairly large chunks appear, or that tiny little Planck-length bits do, which are smaller to an atom than that atom is to the universe, and may be boiling into existence constantly even inside you and I. Space-time contains energy. It's not simply an empty thing we put stuff in, any more than a piece of paper we write on is. We may be able to artificially produce it or harvest existing space-time for power, and we discussed that latter last month in Gravitic Spaceship Propulsion, and ways we might be able to make galaxy-scale megastructures for harvesting dark energy expansion of the universe in our dark energy episode. Tapping early universes or multiverses. It may also be possible to do things like drop a wormhole into a star to suck energy out of it to fuel a power plant somewhere, but wormholes travel through time, not just space, so you might be able to loop one back to the even more energy-dense early universe in its first moments, and indeed that might not violate causality in some models, but even more interestingly, not only are hypothetical wormholes able to travel space and time, they probably work better traveling to entirely different universes. Nor are wormholes the only potential means of reaching other realities or universes. If they exist and can be reached, then many might offer unlimited energy, and as likely as not be entirely lifeless. And while something like that might seem a far distant technology of future Star Trek eras, if it is possible, it may be something we figured out even this century. But whether or not that happens, as we saw today, we have a lot of upcoming energy technologies that are very promising, even if only half of the ones currently on the near horizon work only half as well as seems expected. And as energy is the lifeblood of our civilization, a future of energy abundance seems ever closer,